Alright, let's go over some thermochemical equations. But before that, I want to go over some key information about this exothermic, endothermic stuff. So you have an equation, which I'm going to start as reactants, and then the arrow comes, and then it's the products. Easy way to remember this is you react something together to make a product. Okay, so in an exothermic reaction, the amount of energy in the reactant side, exothermic, reactant side, energy, will be greater than the product energy. And this is logical because if you think about it, when you have an exothermic reaction, the heat exits, so the reactant will have a greater energy, and the product side will have less of an energy because the heat and the product side has separated from the chemical equation part on the reactant side. Vice versa for endothermic, it'll be the opposite because the reactant energy will be less than the product energy. Because in endothermic, the heat enters the specific system you're looking at. Therefore, the end result will have a greater energy because heat has entered your reaction. And with that information, we know that enthalpy is delta H, and enthalpy is the heat that is absorbed or released in a reaction. Absorbed, released in reaction. And RxN is a way of just saying reaction in chemistry terms. All right. So with this information, we can go into our first question. Calculate the amount of heat produced when 52.4 grams of methane, CH4, burns in an excess of air, according to the following equation. And comparing with other chemical equations, this is a thermochemical equation. This is special because right here you can see kilojoules as a part of your equation. And what we talked about here about exothermic and endothermic reactions, we can use to figure out how to solve this problem. So we know that the arrow is here. So this is our product, and this is our reactant, and this is our product side. And if you look here, the energy is in the product side. And what we talked about here was that the reactant energy is always greater than the product energy for an exothermic reaction. So we can see the energy has increased from the reactant side, or it has exited from the reactant side to the products. So if energy exits the reacting side, then the product side will have the energy that goes away. So this thermochemical equation is exothermic. All right. Now we have this information here, 52.4 grams of methane. We can calculate this using our delta H. Delta H is always the change in, the delta means change in. So it's going to be the change in the heat absorbed or released. So in this scenario, since it's exothermic, we have a release of heat, which means that we have to have a negative 890.2 kilojoules in this thermochemical equation. Moving on, 52.4 grams, we set it up using dimensional analysis, 52.4 grams of CH4 methane over 1 times, and then we have to use the grams per mole molar mass of methane. Methane's molar mass is 16.05 grams per 1 mole of CH4 methane. So you want to cancel out the grams of CH4, and we have grams of CH4 on the bottom. Next, we have 1 mole of CH4 that we want to cancel. And this is the special part about thermochemical reactions or equations. You have to use this 1 mole. We have to figure out if there is how many moles of CH4 methane is in the equation given. So if we look here, there's nothing there, which means that there's an invisible 1 representing 1 moles of methane. We just got to bring down 1 moles of methane, CH4. And then on top, we always put 1 mole of reaction, and then we can proceed with our dimension analysis. Then we have to cancel out 1 mole of reaction because there is 1 reaction taking place. And on top, we can put the value for delta H enthalpy because that is how much heat is released in this equation. So negative 890.2 kilojoules. And when you solve this, eventually you'll cancel out everything, including gram CH4, mole CH4, and moles of reaction, leaving you with kilojoules at the end. Multiply everything on top, 52.4 times 1 times 1 times negative 890.2. Click enter on our calculator and divide by 1 times 16.05 times 1 times 1. That will give you in the end negative because we have a negative on here on the 890, negative 2,906 kilojoules. That is our answer. So the key thing you have to remember here is that the reactant side and the product side are separated by the arrow. And if your number is on the product side, it's going to be exothermic because heat is released from the original reactants into the atmosphere with these carbon dioxide and water molecules. And if our number, the kilojoules, is on the reactant side, it's going to be endothermic because you're introducing heat to this methane, CH4, and the oxygen molecules pre-existing as the reactants. All right, number 2. Write the thermochemical reaction or equation for this combustion reaction. When 2 moles of solid magnesium, Mg, combines with 1 mole of oxygen gas, then 2 moles of solid magnesium oxide, and it gives you everything here, magnesium oxide, is formed, and 1204 kilojoules of heat is released. Keyword here being released. All right. So the thermochemical equation looks like the example given in number 1. It's like this, and you always want to have the state of matter in the parentheses. So we're going to start by writing our first reactant on our left side of the arrow. We have 2 moles, so 2 moles of solid magnesium, Mg, 2 Mg, and then do the parentheses S, plus 1 mole. You can write that 1 or you don't have to write the 1. So you can do 1 mole of oxygen gas. Oxygen is diatomic, one of Brinkelhoff, so you have to remember to always have the 2 down there. And oxygen is a gas, it says right there, gas. So we have the parentheses G. And when these two combine, so we have the arrow, 2 moles, so we put 2 moles of solid magnesium oxide, MgO, parentheses S, is formed, and 1204 kilojoules of heat is released. All you got to do is put 1204 kilojoules, and that is your reaction. And as a bonus, let's see if this is endothermic or exothermic. As we calculated or discussed in question 1, the number of heat released is on the product side. And if the product side has the heat, that means that heat was released from this equation. So the energy on this part is going to be released when the reaction takes place, and the result will be 2 moles of magnesium oxide and 1204 kilojoules of heat released. So we can calculate, or we can conclude that this is in fact an exothermic reaction, and the delta H value, since it's heat released, heat exits, is going to be negative 1204 kilojoules. All right. When detonated, delta H of nitroglycerin is found to be negative 5,720 kilojoules per mole. Is this an exothermic or endothermic process? How did you know? What we discussed earlier in question 1 and 2 was that delta H can be positive or negative. In this scenario, delta H is negative 5,720 kilojoules per mole. If delta H is positive, it means that heat was added to the reaction, which makes it endothermic. Now, if delta H is negative, that's exothermic. Heat was released. And in these scenarios, you would see for endothermic, you would see say A plus B in a chemical reaction, and then you'd see a number. We'll say um, let's say 777 kilojoules, and we would have the arrow, and we'd have say AB or something like that. For this one, exothermic, we would have A plus B. The arrow comes, and then we'd have a say AB plus a negative value of 5,000 or 777. Actually, because the negative plays into the exothermic reaction as heat released, we can put positive 777, and you will have to know that delta H is negative 777 because heat was released. That is, in fact, one of the trickiest parts of calculating if it's an exothermic or endothermic, because you do not know immediately, but just by looking at the equation, if just because this is positive number, does not mean it is always endothermic. So your answer for number 3 will be uh, exothermic. All right, number 4. Consider the following reaction of carbon disulfide, which is this right here, CS2, being produced from natural gas. What is the enthalpy, delta H? We're looking for delta H change when 2.5 grams of sulfur is S, is reacted with excess methane is CH4. All right, so when you look at this problem, you always want to start with asking yourself, what is delta H? Delta H is enthalpy. In this equation, thermochemical equation, we know that the value of enthalpy delta H is on the product side because it's to the right of the arrow, and that tells us that it's exothermic. Heat is released from the chemical reaction taking place. Delta H, enthalpy, is heat is released, so it's negative 106 kilojoules. So that's our delta H. Now, the question truly asks us for the enthalpy change when 2.5 grams of sulfur is reacted with excess methane. So we can set it up using dimensional analysis. 2.5 grams of sulfur, 0.5 grams of sulfur will react with excess methane. The molar mass of sulfur is going to be 32.07 grams, and then 1 mole of sulfur. And then we have to cancel this mole of sulfur. So we look at the equation. Unlike question 1, we have a 4 in front of the sulfur. That means that we have to have a 4 on the bottom. 4 moles sulfur. It's like a 5 sulfur. And on top, we have to have 1 mole of reaction. That is going to be standard for all our equations. And then on the bottom, we have to put 1 mole of reaction. And on top, this is the special part. We have to have the calculated value of delta H that we figured out because we knew it was exothermic. You can't just plug in 106 because The equation tells us that he exits the system, so we have to have a negative as here, negative 106 kilojoules. Everything cancels except for kilojoules, and all you got to do is multiply across the top, click enter on your calculator, and divide by everything on the bottom. So you do 2.5 times negative 106, and divide that by whatever 32.07 times 4 is. When you finish calculating that, that should give you negative 2.066, which I'm going to round to negative 2.1 kilojoules. And that is your answer. All right, last question. How much heat in kilojoules is associated with the production of 283 grams of calcium hydroxide CaOH2? Okay, so we have a thermochemical reaction equation given to us, and we can tell that instead of having numbers in our equation, they straight up gave us delta H. When this comes up, you can say, "Thank you, Mrs. Dudley," and accept the fact that this just made your life easier. First, you want to start with 283 grams of calcium hydroxide, 283 grams, CaOH2. All right, the molar mass of calcium hydroxide is going to be 74.1 grams per 1 mole of CaOH2, calcium hydroxide. And the way you calculate this, if you don't know, is Ca, molar mass of Ca, plus we have to distribute the OH, the 2 to the OH, which becomes O2H2. So you're going to have molar mass of Ca plus 2 times the molar mass of O plus 2 times the molar mass of H. Molar mass of Ca is going to be 40.08 calcium, 40.08 plus 2 times oxygen is 16 plus 2 times hydrogen is 1.01. And so add all these together, and that gives you 74.1 grams per mole. That is molar mass. Molar mass of CaOH2, calcium hydroxide. All right, going back to our equation, we have 1 mole of calcium hydroxide. We look at our equation, and in front of the calcium hydroxide, there is no number. That's an invisible 1 there. So we can think of 1 mole of calcium hydroxide over 1 mole of the reaction, which stays constant because we have one reaction. We put 1 mole of reaction on the bottom, and we put our delta H value, which they kindly gave to us, on top, negative 65.2 kilojoules. Multiply all that, which cancels all the units, and all you have to do is 283 times negative 65.2, click enter, and divide by 74.1, and that gives you negative 249 kilojoules. And that is your answer.